Now that we've plotted our slopes on our nullclines, we can look at what's going on generally with our phase plane. Notice that the nullclines divide the first quadrant into 4 distinct regions. We'll call those A, B, C, and D. We can also look inside each one of those regions and get an idea of the general direction of the trajectories of our solutions. Notice that in region A, solutions seem to be pointing up and to the left. In region B, they seem to be pointing down and to the right. In region C, they seem to be pointing up and to the right. And in region D, they seem to be pointing down and to the left. We can look at the behavior of the solutions inside each one of those regions. It should be clear that in region A, that solutions are tending toward the equilibrium 0, 3. Notice that x in this case is 0, y is 3, and because this is a competing species model, what we're seeing here is that y wins because x goes extinct. Looking at region B, we get something similar in that solutions again tend toward the equilibrium. But the equilibrium that they tend toward in this case is the equilibrium 2, 0. In this case, x is 2 and y is going to 0, so x wins, which means that y has gone extinct. Let's look at region C, which is a little bit more complicated. Solutions can do one of two things depending on where they start. They tend toward either region A or B. So solutions here may tend toward region A, whereas solutions that start here may tend toward region B. Once they get into regions A or B, then they're going to go toward the equilibrium points. Solutions technically can go to the equilibrium 1, 1, but that is very unlikely. In region D, we get something similar, and again, that solutions tend toward the regions A or B. Again, that depends on where those solutions start. Here we could see solutions going into region A. Here we could see solutions going into region B. Again, once they get into regions A or B, they can head towards the equilibrium points. And this gives us a general sense of what's going on for the entire first quadrant, where x and y are positive. And we really want to focus where x and y are positive because these are supposed to represent populations. Well, this gives us a sense of what's going on with the equilibrium points as well. It appears to us that 0, 3 and 2, 0 are both stable equilibrium points. And in fact, we saw that these were sinks when we were looking at the Jacobians. But we also have two unstable equilibria. We have 0, 0, which we saw from the Jacobian was a source, and now we can see solutions are all moving away from 0, 0. But we also have the equilibrium 1, 1, which we saw from the Jacobian is a saddle. And we can see that solutions are generally moving toward the equilibrium for a little bit and then veer off into regions A or B. So the question is, what is the long-term behavior of this system? Well, solutions in the long term are going to tend toward one of two equilibriums, either the stable equilibrium 0, 3, in which case we say that y wins, or the stable equilibrium to 0, in which case we see that x wins. And we want to notice that x and y cannot coexist, meaning there is no equilibrium that is stable where both x and y are non-zero. We do have the equilibrium 1, 1, but that is a saddle, and that is not stable. So x and y cannot coexist.